Ladies and gentlemen, a very good afternoon and welcome to the Institute of Advanced Studies Lee Kong Chian Distinguished Professor Public Lecture. I am Abhishek, the Vice President of the Graduate Students Club for the School of Physical and Mathematical Sciences. It is my honor to be the MC for today's public lecture. The lecture is co-organized by the Institute of Advanced Studies and the Division of Physics and Applied Physics at the NTU School of Physical and Mathematical Sciences with the support from Lee Foundation, Singapore. We are happy to welcome our audience here at the Tan Chin Tuan Lecture Theatre. To begin with, may I now invite on stage Professor Chian, Director, Institute of Advanced Studies, to deliver his welcome address. Professor Sam.
Okay, good afternoon. It is very heartening to see that we are back in business, having in-person lectures and public lectures. So let me first, Nobel Laureate Professor Duncan Haldane, Professor Pan Antoine, Chair of School of Physical and Mathematical Sciences, distinguished guests, colleagues, students, ladies and gentlemen. Good afternoon. It is my pleasure to welcome you to the IAS Lee Kong Chian Distinguished Professor Public Lecture at NTU. I would like to convey my gratitude to our distinguished speaker of the day, Professor Duncan Haldane, who is the Sherman Fairchild University Professor of Physics at Princeton University. Thank you for being here with us today and delivering the Nobel Public Lecture. In June 2017, not long after Professor Haldane was awarded the Nobel Prize, we were honored to have him as one of our plenary speakers at the workshop on topological phase transition and new developments organized by the Institute of Advanced Studies at NTU. Today, we are delighted to welcome him back at NTU Singapore to speak to our students and young researchers about entanglement and the second quantum revolution. Renowned for his work on exotic quantum states of matter, Professor Haldane was awarded the 2016 Nobel Prize in Physics, along with David Thouless and John Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. Their work spawned a dominant trend in condensed matter, as we can classify matter with topological invariant without paying much attention to the fine details. Today, the topological framework is used widely for predicting and characterizing new forms of matter. In the first quantum revolution during the 20th century, scientists made use of quantum mechanics to understand what had already existed, such as to explain the periodic table or how metals and semiconductors behave. However, at that time, scientists were not able to design and build quantum systems or manipulate these systems at the individual level. Today, this can be achieved through the second quantum revolution, which is all about controlling individual quantum systems to enable powerful applications of quantum information. Scientists can now create states of entangled matter. These new man-made quantum states have novel properties of sensitivity with far-reaching applications such as the development of next-generation computers, communication systems, and sensors. Hence, we have moved on from merely explaining phenomena in our surroundings to actively employing quantum mechanics to alter the quantum phase of our physical world. Although quantum mechanics as a science has matured, quantum engineering is now emerging in its own right. Entanglement is certainly a central, well-known quantum principle where a measurement of a property localized in one half of a system affects the state of the other half. However, Professor Haldane's research into examining entanglement as a function of its quantum numbers rather than just as an entropy has turned the entanglement spectrum into a powerful tool for detecting and identifying topological order. Now, all of us have much to learn from Professor Haldane's remarkable expertise. His insights are important for the future of the field, and we are excited to learn more about the topological quantum matter and the discovery of unexpected topological states of matter. I hope our audience will be inspired by the tremendous potential that can be harnessed by this interesting field of research. I wish all of you an insightful afternoon. Thank you.
Thank you, Professor Sam. Now I would like to invite our guest of honor, Professor Pan Antoine, Chair, School of Physical and Mathematical Sciences, for an opening address. Professor Pan Antoine.
Professor Duncan, Haldane, distinguished guests, colleagues, and students. Good afternoon, everyone. It's my pleasure on behalf of NTU to welcome Professor Duncan Haldane to deliver today IAS Chian Distinguished Professor Public Lecture. Professor Haldane is currently a Chairman Fairchild University Professor of Physics at Princeton University. For the past 4 decades, he has had a distinguished career in condensed matter physics, making numerous groundbreaking contributions to the theory of the Luther liquid, the theory of one-dimensional spin chain, and more recently, the theory of topological insulators, and in particular, the fractional quantum Hall effect. He had the unique style of not being afraid of marrying abstract mathematical tools with intuitive physical concepts. Many of his ideas go far from original topic where they originally intended to address. And some notable examples are the generalized exclusion statistics and the entanglement spectrum for the strongly correlated many-body wave functions. For the past 10 to 20 years, topological and geometric phases of matters have been one of the most vibrant and productive fields in condensed matter physics. And the interplay between symmetry, geometry, topology shows that abstract mathematical tools, mathematical notions can readily manifest themselves in natural and synthetic materials as well-defined physically measurable quantities. And moreover, symmetry and topology allow us to control and protect quantum information stored in these measurable quantities. And we are thus hopeful for a plethora of novel quantum devices for real-world application in the future. We are thus very honored to have with us today one of the pioneers in topological phases of matters, Professor Duncan Haldane, to share with us his journey in entanglement, topological quantum matters, and the second quantum revolution. He is a recipient of many honors and awards, including the 1993 Oliver Berkeley Condensed Matter Prize, the 2008 Lawrence Chair, the 2012 Dirac Medal, and the 2016 Nobel Prize in Physics. To young scientists in the audience today, I hope that you will leave today's lecture inspired by Professor Haldane and fascinated by delicacy and richness of our physical world. And in closing, I would like to thank the Lee Foundation for its support of this lecture and NTU Institute of Advanced Studies for organizing this event. I would like to convey my gratitude to Professor Haldane for joining us in person and deliver this lecture. Thank you.
Thank you. Oops. Yeah. Okay, thank you for the invitation. I'd like to tell you something about the excitement that's going on these days in quantum mechanics. And the key idea is, what I'm going to talk about is this strange notion of entanglement. There's the key property of quantum mechanics that was actually, as I also pointed out, by Einstein initially as something that was so crazy it couldn't possibly be true, and it's now turned into the dreams of a new technology. And we have this great hope for a topologically protected quantum computer. So the key message I'll give is, as we understand quantum mechanics better, there's lots of new and rather strange possibilities for the materials of the future, and the technologies that they will allow are starting to show up. And this has really emerged through a whole series of unexpected surprise discoveries about quantum materials and lead us to new ways of thinking. So the modern laws of quantum mechanics were established in the period almost 100 years ago by the famous heroes Heisenberg, Schrödinger, Pauli, and Dirac. And the modern laws of quantum mechanics have remained unchanged, essentially. All tests of them have confirmed that they're correct. So no one has built their career on showing quantum mechanics is wrong. Maybe we don't understand it enough to in a deep level, but there's no evidence to the contrary that quantum mechanics is not the underlying law of nature. Okay. So just because we know the laws doesn't mean that we immediately know all that they allow to happen. So as an example, Maxwell completed the laws of electromagnetism back in 1864, and it's taken a really long time for all the things like smartphones and cell phones and all the developments to take place. But it's still something we're learning about in recent years. New developments in electromagnetism, such as photonic crystals, and lots of new laser technology occurring. So it's still, even though the laws have not changed since 1864, it's been a vibrant and developing field. And in fact, back in the early days, I thought it was Maxwell, but it was actually Faraday. Gladstone, the British Prime Minister, who I think before was the finance minister, basically said to Faraday, "This is all very interesting, but what's it good for?" And Faraday is supposed to have said he couldn't tell, but he knows that one day it'll be taxed by you, so. And he was correct. So starting around 1980, new insights into quantum mechanics started to emerge, and new unexpected topological quantum states of condensed matter started to be discovered. At the same time, independently, there was the beginnings of the development of quantum information theory that Richard Feynman had started thinking about in the late 50s. And he started wondering about what would happen when computer technology got small enough you had to get down to the atomic scale and you couldn't ignore quantum mechanics. And he wrote a very inspiring essay at the time called "There's Plenty of Room at the Bottom," because there was a controversial play at the time called "Room at the Top," which is presumably being referred to, but basically saying that lots of new kinds of physics will emerge when we try to starting building devices on the atomic level scale, which must happen in the future, and it is happening now. So what's going on really is, in recent years, is we're learning how to control quantum states. Before, the experiments were more like taking a hammer to hitting something, smashing it, and looking what the pieces were like. Now we're starting to tinker with quantum systems and poke and prod them and try and gently push them to do interesting things rather than just smashing them. And this new emphasis is really why some people consider we're in the second quantum revolution. And I think in the next 10 to 20 years, we're going to substantially deepen our understanding and learn how to use quantum mechanics for new technologies. So it's an exciting period to be around. And of course, quantum institutes are popping up all over the place these days. Everyone, governments and industrial leaders are all getting excited about it. So quantum mechanics, what is it? Back in the original form of quantum mechanics was the Bohr atom, kind of thing that I learned about at school. Quantum mechanics, they showed a little picture of an atom, and in fact, the badge of Nanyang has a kind of somewhere there's an atom, I think, on it. This was a kind of picture of a little planetary system with an electron going around the nucleus. And Bohr discovered that not all orbits of the electron around the nucleus were allowed, and he called the allowed ones orbitals. So there's a name orbital floating around, which goes to this idea of Bohr's orbits of planets going around the sun and electrons going around the nucleus. Well, sometime later, a more correct picture of quantum mechanics emerged. The Schrödinger type picture around 1926, and the Heisenberg uncertainty principle, which turned Bohr's orbit into a fuzzy cloud centered on the nucleus, and learned that we don't exactly know where the electron is at one time, but it's in that fuzzy cloud, and if we try to find out exactly, we're going to ruin the atom. That was the uncertainty principle, that if you do the measurement, you mess it up. But in Bohr's language, so the model for an atom is really a box in which an electron is living. And the name orbital is really what we reserve for the little box which contains the quantum mechanical electron. So we don't know exactly where in the box the electron is, but we can know it's in the box or not. So yeah, this is what you learn in high school chemistry usually. So atomic orbitals, you can see them as little boxes which you put an electron in or not, and it has two states, empty or filled. Okay. And actually, the thing of a quantum state that can be in two possible choices, up or down or empty or filled, is actually the central theme of modern quantum technology, the construction of qubits, which have a state which is two possibilities in a quantum system. So the hydrogen atom is a box, and if the electron is missing, it's just a positive hydrogen ion, and if you put the electron in, it's in this fuzzy box here. Well, actually, we can't see yet the electron in its ground state orbital, but highly excited, when you put the electron in hydrogen into a highly excited state called the Rydberg state, we can now actually take an image of it. So this thing here is actually a real image of a hydrogen atom, and you can see the electron as in an excited state in this kind of cloud centered on the core regions of the atom. And in fact, people work with these things. When you excite them, it becomes quite big, and people start playing around addressing these things with lasers, and a lot of work going on with so-called Rydberg atoms, where you can put the electrons into a rather further out orbital than the one that they have in the ground state. So the key thing, a key component of entanglement involves something called the Pauli exclusion principle. So quantum mechanics is all around us, but we're not really totally aware of it, right? But the Pauli exclusion principle is a very fundamental principle, and it says that two electrons can't be in the same state, which roughly speaking is you can't put two electrons in the same place. And actually, that's why we don't fall through the floor. Newton recognized that there was a gravitational force pulling apples down off trees and pulling us towards the center of the Earth. And he recognized that when we're standing on the ground doesn't open up and swallow us. So there has to be another force acting from the ground to balance the gravitational force. And he just called it the normal force. So if you push down on something, it pushes up, and that's the force on your hand that resists it from going through the material is the normal force. So Newton didn't know what the normal force, where it came from. It was like an obvious thing to him. There was some kind of force that pushed back on you, and this is where the famous action equals reaction principle comes from. But actually, it's the Pauli principle, because why you don't fall through to the center of the Earth is the atoms. There's electrons in the little boxes in the atoms of your shoe, and there's other electrons in the atoms in the carpet and in the floor. And the atoms themselves are 99% empty space. There's electromagnetic forces, but it's not electromagnetic forces that stop you falling through the floor. It's this famous Pauli exclusion principle that says the atoms in the floor are occupied by their boxes are occupied by electrons already, and they just don't want to allow another electron in. So you cannot push the electrons in your shoe, cannot push through the floor, because the ones in the floor say, you can't come here, we're here already. So it's a very powerful principle, the Pauli exclusion principle. So the Pauli principle says two electrons can't be in the same state. And electrons are something called fermions, which it's only fermions that obey this Pauli exclusion principle. And the question is, what exactly is the state of an electron? Well, it turns out that in addition to the position of an electron, describing where it's located and things, there's another internal degree of freedom, which is called its spin. It's like electron is actually like a little spinning top, a gyroscope or a toy top. And it's spinning, and you can use your hand, the right hand rule, to convert the direction of the spin into the direction of my thumb, which is usually called the direction in which the spin is pointing in, although it's really a spin going around this way. And the electron can electron spin can be pointing up, or it can be pointing down. There are actually only two independent states for the spin. So it could be pointing sideways, and the other independent state would be pointing the other way. And you can put two electrons in the same place, provided their spins are pointing in opposite directions. Okay? And the interesting thing is that if I switch the two electrons around, the quantum mechanical state is labeled by, it's actually got a property. It's a complex number. That's a scary thing. I've been teaching complex numbers to entering undergraduates, and they're okay with the calculus, but it's the complex numbers that gets them. But anyway, the quantum mechanical description assigns a complex number, a number which changes sign from plus to minus if I switch the two electrons around. And that's basically because that minus sign, if I tried to add these two states together, it wouldn't work. They would cancel. But the two states could either be, the electrons can be in this state, which is a mixture of up, down, and down, up, or it can be a state, but that's exactly the same state as if they're right, left, and left, right. All you can say is, if I know the electron is pointing one way and the other electron is in the same state, its spin has to be pointing in exactly the opposite direction. Okay. And you've probably seen this if you've done high school chemistry. You get taught the periodic table, as was alluded to in the opening address. And the periodic table is usually portrayed as a set of little boxes. And each box can contain two electrons, one with a spin pointing up and the other with a spin pointing down. And it's like an apartment block with different floors. But as you go up in the building, there are more and more rooms as you get to higher levels. But you basically start filling the building up from the ground floor, and where you get to as you put more and more electrons in determines the chemical properties of the element. Okay, so basic thing is Pauli allows two electrons in each box. And the two electrons are actually an entangled pair. They're entangled because they're in a state which is a mixture of up, down, and down, up. Okay, and it's equal a 50-50% chance of being one way or the other way. So this entangled pair, local entangled pair, entanglement is everywhere then. And in fact, the chemical bond that binds atoms into interesting structures, and like us, for example, is built up of the chemical bond, which is a maximally entangled state where you put two electrons, one up and one down, in a region in between two atoms, and that helps to form the chemical bond that really holds things together. So anyway, the entanglement is everywhere on a local level. But entanglement isn't that interesting if the two electrons that are entangled are in the same place. We can use the entanglement to put them in the same box. But the interesting thing starts to happen if we can keep them entangled as we pull them further and further apart from each other. So it's not local entanglement that's really interesting for quantum technology. It's entanglement over distances. And as I said, entanglement is now recognized as a central property of quantum mechanics, and it was first pointed out by Einstein. And today, before it was a very esoteric and abstract philosophical argument. I mean, early arguments about quantum mechanics center on things like, does free will exist, right? It sounds almost religious, right? Is everything preordained? Does free will exist? When you decide to measure the direction of a spin, was it foretold that you would do it that way, or did you actually make the decision? These kind of very abstract questions were the hallmark of these discussions of quantum mechanics for many years, but now it's turned into something practical, and this entanglement has become viewed as the fuel which will drive future quantum information processors. So most people probably think that Einstein got his Nobel Prize for relativity for his theory of general relativity and gravity or particles moving near the speed of light. But actually, Einstein's prize was actually cited for his early work on quantum mechanics. He discovered the second discovery in quantum mechanics after Planck. He discovered the so-called photoelectric effect, which is something that you can see if you have a garage with a garage door that opens. There's a little beam which of light which shines on a metal, and if it's interrupted by you going through, that stops the garage door coming down and chopping your head off. And that's actually running on the photoelectric effect. So it's practically used. But anyway, so of course Einstein didn't really follow up much more on the quantum mechanics. He got involved in his relativity and gravity theories. And by 1935, he'd actually fallen completely out of love with quantum mechanics. And he noticed that quantum mechanics predicts this strange property of entanglement, which if things were entangled and far away from each other, seemed to him to make complete no sense at all. So he called it spooky action at a distance, and he thought that if you carried out certain measurements, it would actually discredit. If you could do the measurements, you would prove that quantum mechanics was wrong, basically. At the time, of course, no one was able to do those measurements. It took a long time. Einstein was dead before the measurements were done. But he felt that this would get rid of quantum mechanics because it was too crazy to be true. Well, Schrödinger, tried to damp down this debate, and he came up with a much more neutral word. He called it entanglement. And actually, entanglement as a word, it's one of these words, it's a strange word. Every language seems to have adopted a different word for entanglement. In German, it's Verschränkung, it's Intrication in French. So people have to invent new words as new things come along, and it seems like every language has somehow found a different word to use for entanglement without having a common root. Anyway, let's call it entanglement. And what happened in 1935 was one of Einstein's collaborators on this thought experiment called the EPR, Einstein-Podolsky-Rosen experiment. He went public and went to the New York Times, and presumably it was a day where no country was being invaded and not much else was happening. So it made the front page headlines, Einstein attacks quantum theory. And Einstein was furious. He said he never spoke to Podolsky again. He continued to collaborate with Rosen, interestingly, but he said physicists should never wash their dirty linen in public. That was his thing. But he didn't like this being a public discussion, but anyway, this was the flag was planted that this experiment, the EPR experiment, if it was done, would discredit quantum mechanics. And what is that experiment? We said a pair of electrons are in this mixed state of up, down, and down, up. And the idea was basically what happens if I put these electrons in a box, but what happens if I open the door of the box and the electrons are pushing on each other? So if one goes out one way, the other one will go out in the other way because they have to conserve momentum. And so they'll shoot off in opposite directions. And the question is, are they still in this mixed state of up, down, and down, up when they're a long way away from each other? So the question was, the statement is, if I make a measurement of the electron out here and find it's in the up state, it guarantees that someone who does a measurement on the other electron will find it's in the down state. If I try to measure it whether it's sideways, forward, or backwards, it'll be the same thing. If I find it's forwards here, it'll be backwards when the other person does it. And initially, that might sound like it violates the principle of relativity that says no information can travel faster than the speed of light. You do a measurement over here, instantaneously that's affected something over there. But actually, there's no information being transferred. So it's not, in fact, a violation of relativity. I mean, you can easily have things moving faster than the speed of light if you point your laser pointer and it's sufficiently focused and you point it on so it makes a spot on the moon, on the lunar surface, and you move your hand, that spot will travel across the lunar surface. It can travel at speeds faster than the speed of light, but it's not representing any information that someone on one part of the moon is transmitting to someone on the other part of the moon. So it looks like something's moving faster than the speed of light, but there's no information that's actually being transferred. And so there's actually no violation in the EPR experiment, no incompatibility. So there it is. It's a kind of, the particles are in a box. You switch the box off, open the box. The particles shoot off in opposite directions. And Einstein thought that as they take leave of each other, the decision about which one is up and which one is down is already made. And part of the experiments were done where the issues of free will come about is that the modern experiments require that the experimenter has not yet made the decision whether he's going to measure front to back or up to down or left to right until the particles are well separated. Okay, so then that guarantees that there's no trickery involved, and that's unless free will doesn't exist, unless the future was completely predicted by the past, and there was no way that the experimentalist could have, that he thought he was making a free choice, whether it's sideways or upwards that he does the measurement. But I think most people, on a practical level, I think we all believe in free will, so I'm not sure. It's not really worth debating these issues on too great a philosophical thing in quantum mechanics. Anyway, Einstein incorrectly thought that if the EPR experiment could be done, it would show that everything was determined at the time when the pair split apart. And other people kind of made these arguments more precise and came up with more precise experiments. And around about, there were some early experiments in the 70s. And one of the experimentalists, I guess I should have had his photo, one of the earlier photos, one of the people who got the Nobel Prize just recently was Alan Aspect, who eventually got around to doing the experiment where the decision about what measurement to make was not taken till way after the electrons had separated. The earlier one hadn't done that, so he kind of basically drew the line under Bell's theorem and said Bell said that the kind of classical mechanics that Einstein believed in didn't allow something to happen, and the Aspect experiment showed that they did happen. So, okay. So, what's the issue here? Entanglement is great, but actually it's very difficult to keep things entangled over large distances. Because at least for the entanglement in the chemical bond for electrons. So the experiments were actually done using photons, particles of light, where instead of spin up and spin down, you can have light that's polarized vertically or horizontally, which your sunglasses are usually designed to get rid of the horizontally polarization, because that's what reflects from the road surface and causes glare. But more usefully, you can also have a kind of light where the polarization is so-called circular, going round in one way or going round in the other way. But anyway, using modern optical fibers, photons can travel very far without being messed up by the environment. We see photons that have come from shortly after the Big Bang, or at least from the time when the atoms started to form in the universe, and they've come here for 13 billion years, and we see them. So photons can travel a long way, photons of light, without getting messed up. And it started off with experiments under Lake Geneva, showing the EPR entanglement could occur, over a few kilometers, and now it's been done by Chinese team have done it with a satellite in orbit and things. So entanglement of light has arrived. Okay, so what about the information aspect? So classical information is stored in a kind of switch in your regular computer or smartphone or whatever. It's a bit. A switch can either be on or off. And if I have think of it in terms of little atomic magnets, you have a little magnetic region. On might be all the little atomic magnets pointing in one direction, up, and the other ones all pointing down would be off. But the quantum information is not in a kind of large clump of matter like this, but a single spin. And the thing is, a single spin, it could be pointing up or it could be pointing down, but it also could be pointing to the side. There are only two independent states of the spin, right? So if the spin is pointing this way, it's got a finite, and can you compare it to a spin pointing sideways? They're the same part of the time and different part of the time. It's only if one spin is pointing in exactly the opposite direction from the other one that they're in completely different states. So only two independent states, but there's this extra information about what direction they're pointing in. So there's a lot more information carried in this quantum mechanical state than the on-off digital switch. Okay. So classical information is unaffected by reading it out or copying it. So it's actually quite difficult to get rid of classical information. Like if you want to get rid of your old phone, you have to do lots of stuff to erase the information stored in the memory of your phone, so some hacker can't get hold of it and find your banking data. So classical information, you can copy it as many times as you want. But there's a lot more kind of information stored in this quantum mechanical state, the qubit, but it's much more fragile. And one particular important principle is you can't copy it. If you try to copy it, you can make a new copy, but in the process of making the new copy, the original copy was destroyed. So there's a practical, you've got this information, but you can move it around, but as you move it around, it automatically self-erases from where you took it from. So you can't copy it, but you can do something strange called teleportation, which has echoes of Star Trek in it, but quantum information people are now teleporting their quantum information all over the place now. And there you are. So the no cloning property says we can't copy it, but we can start with an atom or a qubit in a known state, which incorporates the state of which is some kind of information over here, and we can take a blank atom which we don't know anything about, and we can arrange things so the information gets lost on the left, but is faithfully transmitted to the right. Okay, and because we're doing this copying, we're not actually. If we try to look what direction the spin is in, we destroy the information. So we're able to clone it and move it around without actually looking to see what it is that we move. And the teleportation thing, this is why remote long-range entanglement is viewed as a resource here. So I've got a pair of entangled qubits, which is like one up and a one down, and a mixture of up, down, and down, up over here. It's called a Bell pair, after John Bell, one of the people who came up with these analyses of Einstein's experimental proposals. So I've got this local one over here that I want to move. Usually this is held on to Alice, and I guess it's Bob over this side wants to receive the information, and there's also someone in the middle sometimes trying to steal it. But what you do here is you have to take this entangled pair and you stretch it without ruining the entanglement. So instead of a local entanglement, I've managed to make a long-range entanglement where I've got a spin at one end, a spin at the other end, but they're in this mixed state of up, down, and down, up. And then I allow it to become, then I allow it to interact with the thing that I want to copy. And after I've let it interact a bit, I make a measurement on this device here. So I don't measure the individual thing. I measure some property of the two spins in the box. And at this point, information has to be transferred. So the person who owns the other end of the entangled qubit has a communication. It's called classical communication. So I have to pick up the telephone line. So I do an experiment over here. I pick up the phone and tell the person on the other end what the result of my experiment was. And then he can use that to recreate an exact copy of the original qubit without knowing what its state is. And the nicely entangled, the long-range entangled pair now is left over as a short-range entangled pair. So I use this resource, the long-range entanglement, to teleport the information over a long distance. Okay, so this is quantum teleportation, which goes on a lot. So how do we produce entanglement? Okay, so any two systems, if you bring them together, will start to interact with each other and become weakly entangled. But we want to get this perfect entanglement where it's a 50-50 superposition of two states. And we want to have the things separable, so it doesn't work. We're not going to deal with chemical bonds or short-range things. And so there's a whole protocol for doing this. We start with two stins with a known reference state. We bring them together in something called a gate, which allows them to interact, and then they start to interact. And we switch this gate. If we know everything about this gate and build it very carefully, we bring them together for a certain amount of time. At a precise time, we switch the gate off, and then the thing has turned into a nice Bell pair. But you have to do this stuff extremely carefully, and you're never going to get it 100% right this way, and it's very delicate. So it's obviously not a very scalable procedure. And this is where this whole topology starts to come in, because we try to come up with a better way to do things that doesn't require us to do very, very precise kind of things. We want to get everything to work without the amount of trouble we have to take to build these very special gates. Okay. So around about 1980, as I said, the condensed matter physicists who were studying condensed matter, which is like solid and liquid matter where things stick together, they kind of came up with kind of couple of weird results. The most interesting one is something called the quantum Hall effect, which was Klaus von Klitzing discovered. And although it didn't seem to have any relation, there was another thing which I was involving spin chains. And it turned out these two things have a lot in common, even though it didn't seem so at the time, and many, many more kind of examples of topological matter, quantum matter, have emerged especially over the last decade. So that's the theme of the iceberg, the huge amount which was hidden before the little peaks which are sticking above the water. Okay. So it turns out that these are weird. The weird properties were basically because entanglement was playing some kind of role in it. Okay. So this is topological matter. So topological matter differs from ordinary matter because it's got some properties that you can label with a whole number. Okay. And ordinary matter is described by boring numbers, maybe like 0 and 1. Something exotic might be -5. But the basic thing is a whole number can't change continuously, right? So if you've got some region which is described by -2 and another region which is described by 0, there has to be some kind of boundary between the two where -2 changes to 0. So you can't go smoothly between different kinds of topological matter. And something interesting has to be going on at the boundary. And that was the key to understanding a lot of this stuff. So topological properties of matter can't change continuously. That makes them kind of robust. You see, the current technology, you see this clean room where all these people are making the silicon wafers. They're wearing all these spacesuits. The spacesuits are not to protect them from the nasty chemicals in the process. The spacesuits are to protect the silicon wafers from little bits of the workers falling on them and making them useless. So a small piece of dust can ruin a silicon wafer. So this whole technology, remarkable technology of today's semiconductors requires this very ultra clean and perfect properties. And at least on paper, the topological idea says that things are more forgiving if you use these protected things. So the classic example in mathematics of topology is counting the number of holes in a surface. So it's telling you that basically the statement is a sphere, a football has no holes in it, and you can change a football into a rugby ball by distorting it, by squeezing on it, but you can't, without some significant damage, you can't change it into a donut by poking a hole through the middle, right? And there's no such, holes come in whole numbers. There's no such thing as 0.3 of a hole, okay? And the famous thing in topology was the great mathematician Gauss. He discovered all kinds of fantastic formulas and stuff. But the thing he thought was the most amazing discovery that he made was the following, that if you take a sphere, you've probably learned in high school that the surface area is 4 pi r squared. And there's a measure of the curvature of the sphere called the Gaussian curvature, which is a product of the inverse of the radii of curvature, whatever, but it's 1 over r squared. So if I integrate the Gaussian curvature over the surface of the sphere, I get 4 pi r squared times 1 over r squared, so I get 4 pi. So that's a kind of trivial thing any kind of good high school student who knows his formulas can get. But what Gauss discovered was, if I squeeze this sphere into a football or a banana or whatever, it's a much more complicated kind of piece of mathematics to calculate this integral, but the answer will always be 4 pi. And it turns out the answer is 4 pi times 1 minus the number of holes in the system. And so if I do it for a ball, I get 4 pi. If I look at the curvature is a product of the two radii in a ball. They're both going in the same direction. If I look on the inside of the bagel, one of the radii of curvature is centered on the hole in the middle of the bagel. The other one is centered in the middle of the stem. So the curvature is negative on the inside and positive on the outside, so it adds up to 0 when you do the integral. If you put another hole in it, I get minus 4 pi, etc. Anyway, so this is a thing. So this is a thing that all the experimentalists who work in topological matter, they insist on showing you a movie of a coffee cup changing into a bagel and back again. And more interestingly, you can find other things, like this is one with 2 handles. It's called a loving cup, which gives you minus 4 pi. This is a strange object with 3 handles. I'm not sure what it's called, but I've heard it said it's sometimes called a California loving cup. But anyway. But anyway, so this formula of Gauss's, what's it got to do with quantum mechanics? Well, it turns out mathematicians love to take a very specific formula and generalize it in all kinds of abstract ways. And the great Chinese-American mathematician Chian in the 40s, he generalized the Gauss-Bonnet formula to a much more abstract formula. It wasn't real curvature on real donuts, but a mathematical curvature in a much more abstract mathematical space. And that turns out to be part of the quantum mechanics. So Gauss is, it's now called the Gauss-Bonnet-Chian formula, and it's sitting here. The mathematicians don't have a Nobel Prize. The rumor is that Nobel didn't like mathematicians because his wife had an affair with one, so he cut them out of the deal. And the mathematicians have a very ageist prize, the Fields Medal, which you can't get if you're over 40. So they've invented a couple of prizes for lifetime achievements, one of which is the Abel Prize, but the other one is the Chian Prize. And Chian's formula is right on the back of the medal that anyone who gets the Chian medal has. Okay. So in recent years, we realized that quantum condensed matter could exhibit unexpected properties associated with long-range quantum entanglement. And what's that mean? So if something is trivially entangled, I can kind of chop it in half, and I can do some measurement on the left side, and it really won't affect anything that's happening on the right side. The quantum mechanical state of a large piece of trivially entangled matter is kind of basically just independent bits on the left and the right. But this topological stuff, it's got some boundary, and if I try to cut it in half, it'll resist cutting in half for a while. But if I manage to pull it apart enough, I will find, once it separates, I'll find the inevitable boundary will now have closed up and the cut will be healed with the new boundary. So the entanglement in there, if I try to pull it apart, the entanglement snaps and it leaves these edge states. And it's a bit like trying to separate the North Pole and the South Pole of a magnet, right? You can't do it, but it's not exactly the same, but something like that. Okay. So topologically trivial states of matter kind of can be assembled by just bringing atoms together like little balls and sticking them. But if it changes to something topologically, something interesting has to happen at a specific point in the process by which when I build this matter together. Okay. So back to boxes I guess this is part of my work, but in heavier atoms, the electrons in a group of atomic orbitals, they actually like to fill these so-called d orbitals. These magnetism comes from these higher levels in the apartment block of the periodic table, and when you fill these rooms up, they prefer, instead of both two electrons going up and down in the same room, they prefer to initially go into their own room and all point in the same direction. And that's how you kind of build up some of these, especially these rare earth magnets that are very strong that you get these days, right? And so the spin is the elementary spin is, for various reasons, is called a half, labeled a half. And so the spins like to go in sequence. And you can see that they build up to they point all in the same direction. They start to become very magnetic. And, but you can see there's either an even or an odd number of these spins in this all lined up in the same direction. So as I say, they all go in the same way till the array of boxes is filled. And the thing was that the thing started with entanglement. In 1981, I discovered that there was a kind of atom where there were two spins in each atom, a nickel atom, where the two spins went into each atom in the two boxes in the same direction. But the spins like to line up when you build them together. You might think they want to be up, down, because they lower their energy a bit by pointing in opposite directions. And people in magnetism had never thought about entanglement in the past. So the picture of a magnetic state, which works in higher dimensions, was basically you just line up these atoms. If you want to pick up paper clips, all the atoms have to have their spins pointing in the same direction. This is a much less obvious kind of magnetism where they up, down, so it won't pick up paper clips, but they still have chosen some direction to point into. The actual state of this system, for when there's a spin 1 but not spin a half, there were two spins here, was this strange thing where there's something like a chemical bond appears that each spin splits into its two partners, which then join up to form an entangled pair linking it to the neighbor. And if you see that, you can see that the atoms at the end of this chain, only one half of their spin went to join the neighbor, so half of it is left over. This is typical, it turned out to be typical of this topological thing, that something strange happens at the boundary between normal stuff and unnormal stuff. And here, although there should be a total spin of 1 in each atom, the last atom has half of a spin floating around, the rest of it being joined up to its neighbors. And so this was a kind of, a big deal at the time because no one had thought about entanglement. But it turns out this principle is still floating around in the kind of materials that people are trying to build quantum computers out of today for the Microsoft attempt. Okay, so let me just move on because it's time. So basically, one of the methods of this is that making progress in all this new quantum mechanics actually requires you to have materials and actually look at things and check that claims that people are making are true. And the remarkable thing that we have these days, we can actually build all kinds of new materials. Instead of making theories to try and mimic real materials, we now make real materials to kind of mimic or bring out, expose the kind of interesting things we find are theoretically possible. So this is material science has tremendously improved. Okay, and there was the meme. Let me move on. So the other thing was the quantum Hall effect. and the other, and that's actually become again a topological thing, a measurement of something related to resistance in a material turned out to be an exact whole number times fundamental constants, the charge of the electron and Planck's constant. So now it wasn't recognized to be topological at the time, but anything that involves a whole number we now know has to be topological, right? And that's what made it robust. So there was a measurement, and they found, instead of a kind of continuous line, they found a kind of staircase where the measurement got pinned at these very flat values over a large range of, in this case, magnetic field. And now the fact these numbers, when you measure it here, are so precise, has actually decolonized the kilogram. The kilogram used to be based on Napoleon. Men invented the kilogram, and they kept it in a cupboard in Paris. And if you wanted to check that your market stall was, giving the right weight for the noodles or whatever, you had to, in principle, send someone to Paris to check your weighing machine against theirs. So the definition of the kilogram was a lump of platinum kept in a cupboard in Paris. But because of these new quantum stuff, we've actually replaced our whole system of measurement. And now you can build something involving the quantum Hall effect and something else to build a device so every country can have its own identical standard for the kilogram without having to worry about comparison with Paris. So this thing, the old one here has ended up in the museum, and this thing you can now, and anyone can have their own standard kilogram, which guarantees the same size, right? So the topological nature of the quantum Hall effect was also a strange thing. It involves electrons in a magnetic field, and if you know anything about that, which maybe you don't, electrons like to go around in little circles in magnetic fields. And it turns out that the nice stuff in the quantum Hall effect is the things go around in circles, but you can see that if they actually hit the edge, they'll kind of bounce around and go around in the opposite direction. So because of this feature, something strange happens at the edge. They go around in circles, and these edge properties, which are typical of topology, are basically underlying this perfect integer thing. Well, this whole quantum Hall effect, where you measure something and you find this very precise integer, grew and grew. And it turned out not just to be an integer, but fractional numbers, which are very interesting. And in fact, an example of the forgiving nature of topological states, which this is the device in which these guys discovered the fractional version of the Hall effect. And you can see they wouldn't get a job at Intel if they showed that as their soldering skills, right? But this thing, you can measure this thing, and it gives you these perfect numbers coming out. So it shows you the forgiving nature of topology. Okay, so quantum Hall effect has all kind of weird stuff. I'm only talking about it because this is one of the hopes for some people's hope for the quantum computing. It has weird things in it like fractional charges, and things go around each other and they pick up strange phases. But the interesting thing was not and this stuff where you have particles moving around each other, and they do, when they twist around them, you get back to something different from where you started on. That's now finally something that a lot of people are trying to realize, and some experiments have started to come out to confirm this stuff. But the most interesting thing is that these topological structures can actually hide information in the structure of their entanglement. Okay, and this is why we would like to use them for quantum computing, because the basic problem with quantum information is once it interacts with the environment, you've lost it. You have to keep it going and protect it till your calculation is finished. And the interesting thing about these topological systems is the information is stored in not at one point or another point, but all over the place in a way that's hidden and exactly protected from the environment. Okay. So the processing of the information in this thing involves little defects or vortices in these. These are little two-dimensional fluids. and moving the things around each other encodes the information. And this is what people have been trying to do for the last few years. And Microsoft have put a huge amount of money into it. Hasn't happened yet. But what we have here is we have a little we have this quantum Hall effect, which is a kind of fluid of electrons with interesting stuff happening at the edges. And in this fluid, you can have these little unexpected vortices, you can have them. And there's a kind of, these objects here, they're a bit like the spins on the end of the spin chain, the two half spins. These are actually half vortices. So these are objects that you can only make by starting with a double vortex and pulling it apart. And when you pull these things apart, the history of how you made them is somehow stored in it. So you have these two vortices used to be joined together, and when you pulled them apart, they left some kind of entanglement, a string of entanglement between them, which records the history of how they were made. And the ones down here were made by pulling those apart. But you could have made exactly the same pattern of vortices by starting with a double vortex here and pulling it apart this way, and then it would leave entanglement patterns and the thing. It turns out that this four-vortex system encodes exactly 1 qubit of quantum information. Now, by staring at it, I can't tell whether the spin is up or down. In fact, the way I've drawn it, this one has the spin is up, or the qubit is up. This one is actually pointing to the side. But then if you start to move these things around and braid them around each other, you actually mess up you mix up their entanglement patterns, and you'll end up moving this thing to point in a third direction. So provided they don't get close to each other, you can't lose this information. Okay. I mean, other things can happen to lose it, but the idea behind it is you can process this quantum information. It's not a little spin that's sitting here up or down. The spin is still there, but it's spread out all over the space inside this fluid. And if someone takes a gun and shoots a hole in the thing, the chances of them destroying the pattern is very small, because the information is stored throughout the system. Breaking a little piece of it will give you, a very tiny chance of destroying the information. So it's protected, and that's the deal which people want. So, so this is a more exotic form of this initial quantum Hall effect, which has now gone into the units, the measure, the kilogram thing. So it's more exotic, but there are states around which people believe is this. There was a large report about something to do with these a few years ago, which turned out not to be true. But it's behind at least one of the efforts for building quantum computers is the Microsoft one, who they've poured some rumored about $1 billion worth of money into this. And anyway, right now there seem to be some suggestions that things are actually happening. We'll see. And so behind this is something strange called Majorana fermions. Again, breaking a spin into two halves, so spin 1 into 2 spin halves, as a topological feature is okay, it's fine, it's not that surprising. But the thing behind this idea for the computers is much more wild. As I said at the beginning, a quantum state could an electron, a box which either contains an electron or doesn't contain an electron is like a quantum state up or down. And behind all this very interesting stuff I was trying to tell you about is that the box, the thing is you can actually, turns out you can pull the box apart and have two half boxes which are well separated. So that's a really crazy concept, right? I've got the electron in a box, it's empty or full, I can kind of look in, I can take a peek at the box, I'll ruin my information by finding out what it is. So to make sure no one can look at the box and find out what electron is in it, I pull this box into two half boxes. And now when the half boxes are well separated, I can stare at the thing and I can't tell whether they contained an electron or not. The only way to find out whether they were filled or empty is to bring them back together again, right? But now, if I've got more than two half boxes, which is basically going back to the picture I showed there, these things are really the half boxes, right? By shuffling half boxes around, I can actually kind of bring different halves together at the end, and I can process this information in a very surprising way, right? I can join two half boxes which were not joined before, and I still get back to the same thing. So to actually get the information out, I have to bring things together and do a measurement, and that's it. So anyway, this is the heart of this idea of the half boxes, which is amazing, called Majorana zero modes, is at the heart of the Microsoft approach. And let me just quickly skip to things. So this is actually a beautiful dream. It's a bit like fusion, right? I mean, on paper it works. Maybe fusion's going to work too, right? In principle, this works, and it gives you it's one of the few things which promises a scalable technology, right? Whether or not it'll happen, people have not managed to make these qubits properly yet. As I say, Microsoft people sort of seem to be claiming things are going better than they were in the past. But it's on paper it works. Lots of beautiful principles work on paper, but it's one of those surprising things that quantum mechanics predicts, and it's a hope for finding new stuff. Just quickly, the thing that they're doing at Microsoft is a superconducting chain. It's not the quantum Hall effect, but the thing was if we couple the electrons in a certain kind of chain, a wire to a superconductor, it kind of splits these little boxes locally into half boxes. And the trick here is that if I do something that splits them into half boxes and then join the half box up with the neighbors, I get left with two remote half boxes, which is actually the same kind of thing as in the original thing of the quantum spin chain. You've ended up with, you have a chain of people, they all hold hands. You think you have a rule that hands come in pairs, but you find out that there's only one free hand over here and one free hand over here, and you've achieved this kind of long-range separation of interesting things. So anyway, so it's one of the ideas. There are lots of different things happening, lots of other approaches, and there's let the 100 schools of thought contend or something like that. There's lots of different remarkable ideas people are pushing for quantum information ideas. The moral of this is that lots of different people have to collaborate. We need like 3 communities really that we have. Underlying this is, people like myself who kind of make simple models of physical reality and try to find someone to build them. There's also discovering the kind of deep mathematical principles that underlie all this, which really is a different kind of thing. And then the most important thing is that people actually build this stuff, right? So it's when you start to bring this kind of cooperation of all kinds of different people together that things start to happen, okay? Oops, going the other way. So anyway, finally, let me just give my motivational message here, right? Most of these discoveries were made accidentally. Okay? Many of the von Klitzing, he wasn't expecting to see this amazing quantum Hall effect. In fact, other people did the same experiment in a slightly different way before, and they didn't see it. He did it in a way that what showed up on his digital meter was exactly the same number each time he did the experiment. So first he thought the meter was broken, right? But no. So you stumble onto things. Some of the things I worked out I never was expecting to find. And the general rule, I think, is the most exciting discoveries in science are things that no one expected to be there, because if there's anything that everyone expects, the really smart people who have gone out have found it already. So the really big discoveries are things which no one knows are there. So you need a luck that your path through science takes you somewhere along these things. You can be walking along a path, kicking the dust, but you have to be looking at what's happening. You have to look down and notice that you've unearthed the great diamond, because if you just walk on by because you're not looking, you'll miss it. Maybe someone else will find it, maybe not. Things usually get found eventually. But so you need luck, but you need to be able to exploit your luck that brings you in contact with something amazing. And I think there's plenty of amazing things out for this new generation of people to find in the future. And this actually sounds like a business school presentation because you need luck, you need preparation, and you need commitment to follow it through. I mean, when I found, if something is sufficiently strange, it gets a lot of pushback, right? I mean, I wasn't able to publish one of my important papers. It got rejected by people who said this is obviously nonsense, right? It was only finally when people actually did the measurements they had to say, my gosh. So it requires a bit of things. So finally, as scientists, we all need to try and communicate what we're doing to the general public. And anyway, there's me trying to communicate science to a politically influential person or something like that. Thank you.
Thank you, Professor Haldane, for sharing your interesting work with us. May I please request you to be on the stage, please? Now, I would like to invite Professor Yangbo on the stage to be the moderator for the question and answer session. Professor, please.
Thank you. Do I have one?
Okay, good afternoon, good evening for everyone. My name is Yangbo. I'm an assistant professor from NTU. So thank you again for the very stimulating talk. Now we are opening the floor to the audience. So if you have a question, just raise your hand. We have people running around with microphones. Okay, yes, we have the first question here. Yes, I think we have microphones, right? Can we? Raise your hand, just raise your hand, yes. Okay.
So hi, Professor Duncan. Thanks for the brilliant presentation. And my question is about quantum entanglement. Mm-hmm. I'd like to ask your opinion about one perspective trying to explain the possible reason why quantum entanglement can happen between a long distance. And the perspective is like this. We think quantum entanglement happens long distance, but it doesn't. It may happen zero distance. We think it's long distance because we see it from a three-dimensional perspective. It may happen to be zero distance at a higher dimension. To give a simple example of this, let's say we have 2 points on this paper. And in this two-dimensional space, they have a long distance, 2 points, right? But if Professor Duncan, can you kindly help to hold this paper, maybe? Yes, maybe hold it steadily, yes.
Sounds like you're making an Einstein-Rosen wormhole.
Yes. So something like this.
Yeah.
In two-dimensional space, these 2 points share a long distance. But in a higher dimensional space, if we warp it into three-dimensional and we make a hole like this, then they are zero distance. And that's where entanglement happens. So I'd like to maybe pick up your brain. What's your opinion about this perspective?
You'll have to ask Lenny Susskind, but yeah, I mean, there's a lot of people from the high energy and the community and string theory community have moved into viewing quantum information as the solution to understanding, the nature of space-time, and lots of ideas floating around that community that space-time is actually held together by entanglement, basically, and that space-time as we see it or as we experience it is an emergent property from a foaming bubble of entanglement, and which is the idea, I guess, that you were mentioning in the talk, right? That the wormhole, Lenny Susskind has been pushing the idea of the Einstein-Rosen bridge as the same thing as EPR. There's a story in that community that says EPR equals ER, which is Einstein-Podolsky-Rosen. He went on to write a paper about wormholes just the next year after that, which apparently seems quite different, but this idea that entanglement and wormholes is somehow right. But I guess I'm much more prosaic to actually looking at trying to build stuff out of lumps of really interesting pieces of matter with spin orbit coupling, and to actually assembling it in the lab. The problem with the wormhole and stuff, it's very theoretical, and I'm not quite sure. I haven't found the right team of people to build me the wormhole yet.
Okay, very interesting question. So if you're interested, you can also search for ER equals to EPR on Wikipedia or Google. It's an interesting topic. Okay, do we have another question? Just raise your hand. Yes? So maybe I can break the ice a little bit, ask a non-technical question. Mm-hmm. In the last slide, you mentioned that for scientists, we need a little bit of luck. Mm-hmm. Can you recount some of the luckiest moments you have, the eureka moment over your career of research?
Well, I mean, most of these, there's about two things I could point out. And, well, I mean, yeah, so some of the things that were mentioned, the issue, there was something called entanglement spectrum. It only emerged when I got around to actually having it some interesting data plotted, right? And if it's just a load of numbers or something, it doesn't mean anything. And suddenly, if you print it out as a picture, suddenly you see something. So you actually, you find things unexpectedly sometimes, right? And the spin chase stuff was completely just emerged from some other work on one-dimensional conductors and things, and someone suggested you could apply these same techniques to looking at these problems in magnetism, and I was as shocked as anyone else to find one of the two pictures I showed was the standard picture of magnetism at the time, and the idea that the size of the spin could matter, right? Whether spin one is just bigger, a longer spin than spin half. As you add more spins to it, you make your magnet more strong, like the neodymium magnets that you can buy these days, right? Really strong rare earth magnets. And there's sort of just a kind of change in the size of things, but actually the spins themselves, the magnets are built out of putting little spins in a whole number of spins in the atom, and the fact that putting an even or odd number of spins should make a difference was completely unexpected. I mean, I was as shocked as anyone else, right? It only emerged if you look at a problem from some new viewpoint, it's either very useful, it gives you another way of thinking about the problem, but very occasionally it shows you something was wrong before. And the more different ways you can look at the same problem, it's very useful. But if the different ways give you different answers, then that tells you something has to break somewhere. Yeah.
Seems the luckiest moment is the Haldane gap in the spin chain, so something you can also Google about as well. Okay, so any other questions? Just raise your hand. Yes, we have one question here.
Thank you, Prof. Haldane, for the insightful talk. So I want to ask about the issue of scalability in quantum computers. So we know that a lot of big companies are using superconducting qubits, but there seems to be a soft limit on the quantity of qubits that they can have due to issues like error and all that. And then it's really difficult to create logical qubits. Do you think that to solve this issue, there has to be new discoveries in engineering, physics, or in any domain, or is it do we have to completely reconsider how quantum computing is done, or
Well, yeah, but all these things have probably maybe need to happen. I mean, the current state of things is that you got your quantum computer and it interacts with the environment. You do your best to kind of protect your qubits, isolate them, and maybe have multiple ones that you can. I mean, one thing is to have start with 10 copies, for example, 10 to start the computer 10 times, 10 samples, and you can check. You're not allowed to find out what they're doing, but you can check if one of them is doing something different from the others, right, without measuring it. And so you go along and you see one of them doesn't seem to be the same as the others, so that one obviously had a mistake, so you throw it away. you go on a bit more time, another one drops out of the thing. You've got to make sure you've got more than one going at the end and get the same answer out of it to have any idea that you got the right answer, right? So the problem is, without any special protection, the rate at which the errors occur will just be linear in time, right? The longer you run it, there's always a chance of an error. So the trouble is that means that the outcome will fall off. So the current strategy is something called, I guess, NISC, noisy intermediate scale quantum computing, where you try to make your qubits as good as possible, and probably the strategy is you repeat the calculation a number of times, and if you get the same answer more than once, you declare that has to, maybe you get the answer same answer 3 times, you can be kind of sure that something didn't go wrong along the way. But clearly, if you just run this thing and some answer comes out, you've got no idea whether it was correct or not. You've got to have some. So the idea of the nice on paper idea of the topological computing strategy is that you still have some danger when you put the information in. These vortices or these Majorana zero modes, these half boxes, they have to be close together for you to put the information in, right? And eventually, you've got to bring them together again to get the information out. So when they're close to each other, you've got a possibility of losing stuff. But at least on paper, the idea is that when they're far away, you can move them around. So the computation is not in danger, provided you keep them far away. So you don't have the same constraint on the running time, right? Read in and read out are dangerous, but on paper at least you can keep on going for a lot further, making your calculation more and more complicated. But the current strategy, I guess, is get 50 qubits or 50 or 100 qubits or something like that, and hope you can some computation is simple enough that it gets through to the end without getting lost. So it's like keeping your fingers crossed. I say if you get the same answer more than once, you can declare that has to be the correct answer, because the chances of the 2 answers being the same is so small. If
Thank you.
Errors happen, yeah.
Great, thank you. Let me ask you a question from one of the students. You probably got asked this question quite a lot. I wonder if you have a short answer for that. The question is, what makes a good researcher?
Well, I don't know, I guess passion, really. I mean, you don't go into this, life for money. I mean, a lot of people ended up, certainly in down periods, a lot of people ended up getting swallowed up by the financial industry, and they went off, their scientific career stumbled, and, they were earning a lot more money than they were getting in their scientific career, but these guys all had regrets about, a lot of them come back and try and, dump money and fund things, right? I mean, it's a passion, right? I mean, to make something work, you've got to put your heart into it, I guess. I mean, you have to have the ingredients of luck, which is partly you don't know what's going to happen in your scientific career. It depends on where you end up studying, who's there, what problems you get into. The one advice I give to people, I think, is to keep your ears open for new things, right? So if you start off go to university or go to graduate school or whatever, there'll be all these seminars going on and people coming and telling you about work. So the fact they got invited to give a seminar probably means that what they're working on is interesting or currently interesting, and maybe you won't understand much of it, or maybe not understand the word, but you get some kind of feeling, and maybe at the beginning of the seminar, if it's good, some kind of introduction, and also, so expose yourself to different things that are going on, and sometimes you actually may feel that something you know about from some other area actually might be applicable to this completely different problem that the person in front of you is talking about, because certainly in physics, we find the same general principle of quantum mechanics, for example, applying condensed matter, particle theory, and all kinds of statistical mechanics is related, and so lots of different areas of physics which don't apparently involve the same physical material end up having the same general principles. So ideas in one area can actually give you one of these new ways about looking at a different problem that the people in that field hadn't been doing. So keep your eyes open and go to seminars, and even, you can always take some worker with you and be working on it if it's a boring seminar and you can't leave in the middle without being embarrassing people. So, but just expose yourself to things that you didn't know about, and who knows what kind of interesting directions people go. So people branch into different ways, and so a scientific career is very unpredictable, right? It's not really like if you're in an engineering thing, you're working on some project and you probably have to follow a straight line. But again, if something interesting shows up along the way, the important thing is that you're able to at least be able to spend a little bit of time, seeing if there's anything really worth something there that needs to be looked at more, because that's where the unexpected discoveries come. You want to be able to be open to using your curiosity to find out, why did this happen? Right?
Okay, thank you very much. Okay, any more questions? Yes, question over there.
Thank you for your talk. In fact, in your talk, you mentioned about the scientific disagreement and how healthy they are. And you cited the EBR paper and then the long discussion between Bohr and Einstein. Mm-hmm. As we know, this discussion started in the very beginning. It was really philosophical discussion. Then with time, it became mathematical and finally experimentally tested idea. This seems to suggest that disagreement in science is really nice, especially about quantum mechanics. Now, this brings me to my question. Now, in quantum mechanics, we still have some questions that nowadays they still seem philosophical, specifically the question of the interpretation of quantum mechanics. Now, if I would learn from history, I would say these discussions are really healthy and we need to pursue them further. But I'm not sure if history can repeat itself again. So if it worked in the past, it might not be fruitful in the future. So my question for you is, what is your personal point of view about such discussions and debates about the interpretations of quantum mechanics? Especially the ones that are really now far from experimental tests.
Yeah, discussions or ideas are always interesting, right? I view myself as a kind of quantum mechanic rather than a philosopher, right? Trying to actually do something practical with quantum mechanics and understand things on the small scale in some way, right? The big picture, sure, but whether is wormholes, is entanglement in, is space-time held together by entanglement, and very interesting ideas, right? But a lot of work on quantum black holes in the community now, and it changes from time to time. There was something called a firewall, and all sorts of things happening there now. So yeah, it's great there's people thinking of these ideas, right? But it's also great that people are actually trying to see what actually happens in a lab and trying to realize some of these crazy ideas that come out and build something. And in the end, testing the work I did, which was this little thing about the spin chain, which turned out to be it got people so angry in the community that because it clashed with the previous ideas, but it started a controversy, and a tremendous amount of important techniques were developed, both experimentally and theoretically and numerically, to test the thing. Once something gets controversial, people get interested in seeing whether they could add their 2 cents worth to this thing, and some of the important techniques based on which we now realize involve quantum information, so-called matrix matrix product renormalization group and things started off actually as attempts to test this idea about whether there was this new state of the spin 1 chain was correct or not. And then experimental techniques were devised too. So a controversy is actually extremely good in science. It gets people interested. Lots of different people come up with different ideas. And if you want to work out for yourself whether something is true or not, and you come up with some method that you think might do it, that method is probably going to be very useful for other things too. So I think science is totally boring if there's no controversy, right? So controversy is really a great, the thing that causes things to happen, right?
Thank you very much. Any other questions? Yes, we have a question over here. Can we have
Thank you, professors. I want to ask one question. What is your inspiration, or what inspires you to study topological quantum matter, or study there are many branches inside physics, and many of which already been studied, or many of which are still new branches. What made you to choose this specific branch?
Well, no, it wasn't a deliberate thing. It was accidentally stumbling over this stuff. To get into condensed matter physics, actually I had a lucky break at the beginning of my career. I had to choose between two professors to work with, and one of them was actually worked on string theory. But it was string theory in 1973, when string theory was supposed to be a theory of quarks and hadrons. And about 6 months after that, string theory dropped. It became clear it was not a theory of the hadrons, and it became dead for 15 years. It's called the wilderness years of string theory. It was only resurrected by Edward Witten and Polyakov in the 1980s. So I don't know if I'd gone into studying the massless rotating string, which was explained to me, I'd have ended up in a bank or something like that. Because the market for people, well, I've had to reinvent myself to find some other thing to go into. So yeah, scientific decisions are a kind of, who knows where they take you, right? You just have to do, well, that's the whole thing. You take advantage of whatever opportunities come your way, right? And hope for the best, right? And be flexible, be ready to change. But yeah, it's difficult. Very few people, I think, start with a definite program, right? And say, I'm gonna go into this area. You go into something because you heard something interesting about it, and then you felt maybe you could contribute in some way. Or just interested enough to explore it. And so yeah, I don't think you can plan your career at all. You have to take advantage of what life offers you, and what's happening, and what problems. It's important to work on a problem that people are interested in, I think. If too many people are interested in it, there's too much, lots of competition. But if no one's interested in it, you're not going to get any feedback. I think communication in science is important. Some people, Einstein supposedly could sit around working by himself. I'm sure Einstein had lots of interesting discussions and letters with people. Right? You can't work in a vacuum. You've got to find out what's happening and get ideas from other people and listen to ideas and choose some idea to work, something to work on, but also be prepared to move to something else if things aren't working out. It's hard to say how to. You have to put your heart into it, basically, I think. Yeah.
Thank you.
Thank you. So unfortunately, the bus is waiting outside. We can't entertain more questions. So let's take this opportunity to thank Professor again for the very nice session.
Okay.
Thank you, Professor Haldane and Professor Yangbo. May I request you to be on the stage for some time? I also kindly request the audience to be seated at their places. Now for the photo taking session, may I kindly invite our VIPs to join Professor Haldane and Professor Yangbo on the stage.
By the way, for the photo session, I did bring something along.
I see.
So maybe selfie, it might be selfie time, I'm not sure.
May I invite Professor Fan Anton, Professor Samje Chan, Professor John Pablo Ortega, Professor Liu Wenxiang, Professor Albert Chia, Professor Guan Yong Liang,
Anyone in science has a chance to get one of these, an extremely tiny chance because it needs the luck. You know, you don't have to be a smart guy, you have to be a lucky guy, right? To find the right, smart people do fantastic work, but you know, if they don't get the luck, they're not good. So anyone working in science and they're able to just take the time to look at anything interesting that comes along, there's a very, very tiny chance it might be one of these fantastic things, and so that's where these things come from.
Thank you.
Thank you.
I would now like to invite Prof. Fan Anton to facilitate the presentation of Memento to Professor Haldane.
Thank you.
NTU symbolic building.
Okay. Thank you.
Thank you, Prof. Haldane. Thank you, Prof. Fan.
Yes? Oh. You want to sit? No, you stand. Stand here. Sit down, stand down here.
Yeah? Okay. The group photo with the audience.
Yeah.
One step.
All three.
Sorry.
Okay. Thank you. Okay.
So this brings us to the end of our public lecture. I would like to thank everyone for your presence for this public lecture. May I invite our guests to remain seated while our speaker and our senior management take their leave.